Okay, for day 2, we're going to look more at wires. So in the last day, we saw that if we have a wire, like so, and we have a current traveling through a wire, if we take our right hand, wrap our fingers around it with our thumb pointing in the direction of the current, it will tell us the direction of the magnetic field. So my fingers are going to curl behind and around it, like so. So it's going to create a magnetic field like this. Okay, that will be my magnetic field, and that's my current. The strength of the magnetic field is inversely proportional to how far it is away. So what that means is that the magnetic field here is going to be a lot stronger than the magnetic field out there. That's pretty obvious. Just like in gravitation, the further you are from a massive object, the less gravity you'll experience. Same thing for a magnetic field. Okay. So an equation that results is the following. Magnetic field is equal to this mu naught symbol multiplied by current divided by 2 pi r. So this mu naught, this is called the permeability of free space. So it's basically describes the ability for a magnetic field to form in space. When we're talking about mu naught, that's just in like a vacuum, empty space. There's different values if it's in air and water, etc. So, but you'll just have to worry about this. In the ideal situation, space, that's what it is. Okay. So the value for mu naught is equal to 4 pi times 10 to the negative 7 Tesla to 7. So let me just write that again to make it clearer. So negative 7 Tesla meter amps. Okay. And oftentimes it's might be written like this: mu naught over 2 pi. If you just divide that by 2 pi, you get 2 times 10 to the negative 7 Tesla meters per amp. So those are our two values. Why is it a pi? Well, you learn more about that in university when you figure out more about like calculus. Because it's to do with a circular path, we get that pi in there. We know that pi is to do with circles, and again, you'll learn more about that in university, depending on if you take the appropriate math courses. So if we scroll down, we can see some results of this. So if we have a magnetic field outside a long straight wire, so let's say we have two wires that are parallel to one another. So let's say we have current traveling upwards in both. By having these wires in close proximity of each other, they'll actually experience a force. So let's see what type of force, like what's going to happen to these ones. So if we have, let's just look at the left wire first. The left wire has a current upwards. So I take my right hand, I put my hand around that left wire. We say, the magnetic field is going to go around the wire like so. And that field goes all the way. We see that when it's over here, it's going to interact. That magnetic field is going to interact with our right wire. And what we'll see is that, so if we kind of trace this path, like the magnetic field is traveling left, let's get a different color, traveling left, then coming out of the page, then traveling right, then it's going into the page, then it's going left again, then out of the page, then into the page, and so on. So at this point, right around here, we can represent the magnetic field as into the page, like so. So now if we use our other right hand rule, we say, the current's pointing up, so my index finger points up. My magnetic field is into the page. So where's my thumb pointing? My thumb is pointing to the left. So here's my index finger, there's my thumb, and there's my other fingers. Oh yeah, that's a long index finger. But my thumb is pointing in this direction. F. Force. So you say, okay, this wire on the right is going to experience a force to the left. So let's see what happens if I look at the other one now. So let's look at this other wire. The magnetic field is going to be around the wire like so. So if we kind of trace that again. So again, current's going up. My fingers point around, so it's going left, then out of the page, then to the right, then into the page, and left. So right here, the current is coming out of the page. So if I use my other right-hand rule now, say, okay, my current is pointing up, so there's my index finger. And my magnetic field is pointing towards me. I don't really know how to draw that fingernail and finger towards us, but it's a tough one to draw. And my thumb is going to be pointing to the right. Huh. So my force experience is going to be to the right. So all in all, what we can see is that this one experiences a force left. This one experiences a force to the right. So when you have two currents, like two wires that are near each other with current flowing in the same direction, they're going to experience an attractive force towards each other. And this also goes back to Newton's third law: for every action, there's an equal and opposite reaction. So if the one wire is pulling the other towards the south, that means the other one must be doing the same. So if one's pulling to the left, the other must be pulling to the right. Guess what happens in this one? So same idea. We have that current's traveling around. We say, right here, it's into the page. My current is down. My field's into the page. My index finger points down for this right wire. Magnetic field's into the page. We would get a force that is to the right. So in other words, what we can see is that into the page, we end up with this repulsive force. You get this repulsive force in both situations. So when they have two currents going in opposite directions, they're going to repel one another. Okay, so let's scroll down. So remember this equation from last day. F is equal to ILB. But basically the current of 1 creates a magnetic field, which will then interact with the other wire. So if we combine our various equations, actually I need to scroll up. Here we go. So here's our equation we saw just today. We said, so the first wire creates a magnetic field. We'll call that B1. And the magnitude of the magnetic field is going to be the mu0 I1 divided by 2 pi L. So the force that the second wire experiences is going to be the current traveling through that second wire multiplied by the length of the wire that's inside that B1. So if we combine these two equations together, we can see our force is equal to, just going to substitute that B right in there. So we get mu naught L I1 I2 over 2 pi L. So this will give us the force that one of the wires experiences. Again, if you find the force of one, you know the other must be the same because of Newton's third law. So if we look at our example down here, we can use that exact same formula. We say that, okay, we have two wires that are next to each other. We say, okay, we just plug it right into our equation that has that mu naught L I1 I2 over 2 pi L. We can rewrite this as mu naught over 2 pi, and that's going to be L I1 I2 over L. Two different L's. And it says calculate the magnetic force between two 5 centimeter long wires. Alright, so we have to make sure you don't mix up which L is which. So one L is going to represent the length of the wires within the field. The other L is going to represent how far apart they are. So now I can just plug in my values. Say, okay, that's just 2 times 10 to the negative 7 Tesla meters per ampere. And little L the 5 centimeter long wires, so we get 0.05 meters. And our two currents are 8 amps, so 8 amps times 8 amps. And they are 10 centimeters apart, so 0.10 meters. And we get a force of 6.4 times 10 to the negative 6 newtons. So again, the calculation, very straightforward. Just plug it into the formula. But we're not done yet. It's going to be towards each other or away from each other. So then we read their question. It says, in the same direction. So if we look back to our previous example, we saw that in the same direction, they're going to experience an attractive force. So towards each other. Again, we can always just, don't have to memorize it, just draw it out again. Here's our two wires, current. And if you find out one, you know the other. Going to go around it. So you say, the magnetic field is into the page. Our current is up. Our force must be to the left. So our force is towards each other.